Good afternoon, everybody. Welcome back to the 2 days. Good afternoon, everybody. Welcome back to the 2 days webinar on materials and their applications by the Department of Physics and Chemistry, SSM IIT, Dindikal. Our next speaker guest is Dr. K. Sundaravel, Assistant Professor, Department of Chemistry, Bharatiyar University, Coimbatore. It's my pleasure to introduce Dr. K. Sundaravel, who is going to speak about molecular devices for the degradation of aromatic pollutants using dioxygen, a biomimetic approach. Dr. Sundaravel has finished his graduate and postgraduate in Madurai Kamaraj University, Madurai, and he has completed his PhD in Bharathidasan University, Tiruchirappalli, under the advice of Professor Dr. M. Palaniyandavar. And he is a postdoctoral researcher under Professor Dr. Wu Nam at Center for Biomimetic System, EWA Women's University, Seoul, South Korea. He has won DST Innovation in Science Pursuit for Inspired Research Faculty Award and joined CSIR UGC Junior Research Fellow Award. His research area is bioinorganic chemistry. I feel we are all lucky enough to have such an eminent personality as our guest speaker. Welcome, sir. Sundaravel, sir. Sundaravel, sir. Sir? Sundaravel, sir.
Yes, ma'am.
Welcome, sir. You can start, sir.
Yeah, thank you, ma'am. So, respected participants and students, it's a very good afternoon to one and all. And also, by the starting itself, I wish to thank my friend Singaram for giving this opportunity to present our part of the work in the virtual conference. So, I am working as assistant professor at Bharatiyar University, which is located at the foothill of Mardamalai. And Bharatiyar and Bharathidasan University both are started the same year. So our chemistry department as well as the university is one of the vibrant institution. So our group is mainly focusing on small molecule activation as well as bio-inspired and bio-inorganic catalysis. As we are inspired from the nature, we are involved in the designing of small molecule models to mimic the enzyme functions. So one of the approach what we are using is exactly mimicking the functional models for proteins which are present in nature and catalyze a diverse range of reactions which are having some biological importance. So in this aspect, we are working. So today I am going to present my talk on the topic molecular devices for the degradation of aromatic pollutants using dioxygen, the biomimetic approach. So let us give a preliminary introduction that we well known about these things. So we well know that environmental pollution, these pollutants are highly toxic compounds which are harmful to the all form of life which is existing in the globe. So and the sources for the toxic pollutants are nothing but day-to-day our activity is responsible for those kind of pollutants. We will know that chemical industries and pharmaceuticals, they produce a large quantity of xenobiotics as well as polymers, and the paper pulp and bleaching action generated a huge amount of chlorinated organics, and due to the mining and the fossil fuel activities that involve the heavy metals, the higher usage of fertilizer and pesticides in agricultural bodies, that also cause the major pollutant. This aspect, if you are seeing what will happen once the pollutants are accumulated in nature, they can easily be biologically activated. So because since they are aromatic molecules are harmful, they can easily be activated and that generate the reactive intermediates such as catechol and epoxidase. These epoxidase undergo easily opening reaction in presence of the reactive species, as well as catechols are redox active organic molecule. So that can easily undergo oxidation, 2-electron oxidation that will result in the formation of quinones. So at this vulnerability, what would happen? The oxidizing agent or molecular oxygen that is present currently in the nature that can easily be activated by accepting the electrons. So 1-electron reduction will lead to the superoxide species, upon 2-electron reduction will lead to the peroxide species. These two form of oxygen is a highly reactive form and that will conduct a wide range of reactions. If they are bound with some other metal sites, they will do the oxidation in a selective manner. Meanwhile, if they are present free, that is a free superoxide is generated or peroxide is generated, they will randomly undergo reaction with the biomolecules. So that will lead to the mutation. Mutation is nothing but the inactivation of proteins or lipid peroxidations that will generate the harmful products. So what we should do? We have to find out a solution to degrade these pollutants which are harmful to the living things. So then a big question mark will arise. So whenever we are having questions, so we can get simply the answer from the nature. So nature is a superior power that can give the solution for every troubles what we are facing on the earth. So nature can do anything with the aid of all the available plenty of resources. So it is a bacteria is one of the Trojan warrior used by the nature to degrade the pollutants. So during the bioremediation processes, bacterial enzymes play a major role. If you are seeing in this slide, that will clearly give the picture about the nature of the pollutants, how they are undergo the metabolism. So in the outer circle, if you are seeing, there are a lot of aromatics, that is nitro compounds and alkylated compounds and chlorinated compounds, they are present. In the inner circle, what would happen due to the some other enzymatic functions, they are converted into dihydroxy bases, nothing but the catechols or polyhydroxy derivatives. These derivatives are further undergo degradation by the use of the catechol dehydrogenase enzyme, which is responsible, takes place in the, it is playing a vital role in the last step of the degradation of all the aromatics. Whatever may be, that will be finally converted into hydroxy aromatics, and the hydroxy aromatics undergo degradation. So this catechol dehydrogenases contain iron in their active sites. So before enter into the enzyme function as well as the structure, we should just recall some of the factors what we have already learned. It is the fourth most abundant element in the earth crust, and it exists in the two major oxidation state, +2 or +3. And among the two oxidation state, +3 is the highly stable oxidation state, the D5 electronic configuration. In addition to that, in all form of the life exists on the earth that utilizes iron as one of the important metal for the metabolism. The second one we should know about is every human body is containing about 3 to 4 grams of iron in there, which is needed for their biological function. So these iron enzymes can easily be classified into two types based upon the active site structures. If they are having the heme active site, they are called as a heme enzymes. Whereas the non-heme active sites, instead of porphyrin, if you are having a protein recipes such as carboxylate glutamate or aspartic acid or histidine or the cysteine or tyrosine, whatever we are having that is making the coordination geometry around the metal, that can be easily classified into non-heme enzymes. Non-heme enzymes can also easily further classified in subdivided into two types. One is oxygenases, another one is electron transferring enzymes based upon their functions. So as we are focusing on the oxygenases enzymes, these oxygenases also further subdivided into two classes, monooxygenases and dioxygenases. From the name itself, we can easily come to understand the meaning of that word, monooxygenases. Both the enzymes activate molecular oxygen, but the function, biological function is entirely different. Monooxygenases activate the molecular oxygen and insert only one oxygen atom from the molecular oxygen into the product. Whereas the second oxygen atom will be converted into or reduced into water molecule. In contrast to the monooxygenases, dioxygenases are entirely playing a different role. In this case, there is no water formation is observed. Instead, what would happen? This will activate the molecular oxygen and insert both the oxygen atoms into the substrate and give the oxygenated product. The representative examples are right down here: catechol dioxygenases and naphthalene dioxygenases and lipoxygenases, and so on. There are a quite large number of enzymes are available to do these functions. Why we are focusing on ion enzymes? Ion is one of the important element for the living things which is existing. So without that, there is only a few animals can be present, but almost all the life form that utilizes iron. So iron also having some structural, functional diversity depending upon the change in the active site as well as the change in the ligand donor arm that can play a wide spectrum of reactions. We well know about the hemoglobin. Hemoglobin is nothing but the iron porphyrin core, which is ligated with the histidine imidazole in one of the position, and it play a role in biological system as an oxygen carrier, to transfer the oxygen from the lungs to our tissues. If you are replacing the histidine imidazole nitrogen donor arm by a cysteine sulfur, that function is entirely different. Again, the heme active site is retained, but their role is entirely different. P450 is responsible for the hydroxylation of organic products. Suppose if we are entirely changing from the heme active site into non-heme site with the cysteine ligation, that the ion functions is entirely different. It's in case they are having the porphyrin core, it will act as a oxygen activating molecule, whereas if you are having a non-porphyrin core, it will act as a superoxide reducing agent. So further, if you are removing one or two ligated sites, then if you are generating more vacuum sites or level water containing sites, that will mainly involve in activation in the non-heme environment with the non-heme environment. So these non-heme enzymes are highly important. Here you can see a few examples where the biological reactions are carried out by the non-heme ion enzymes: hydroxylation, ring opening, ring closing, desaturation, all epoxidation, so on. So there are a large number of reactions. Only I have represented some of, I have shown you this particular reactions only. So these enzymes are highly interesting. So let us enter into our ultimate aim as the bioanalytic chemist. We focus on the active site. So we have gained more insight into the active site. The protein part is not much contributing on the reactivity, mainly the active site will play a major role in conducting the reactions. So the catechol dioxygenases are nothing but the mononuclear iron proteins with the iron 2 or manganese 2 and the iron 3 containing active sites. They are mainly found in soil bacteria, so they are mainly involved in the bioremediation of the aromatic compounds. So what is their function? They can simply oxygenate the dihydroxybenzenes by inserting both the oxygen into the substrate, the catechols, the so-called catechols. They are classified into two types based upon the ring cleavage. The catechol ring also undergo two different modes of ring cleavage that we are going to see, and they will classify into two types. One is the extradiol cleaving catechol dioxygenases, another one is the intradiol cleaving catechol dioxygenases. In both the enzymes activate molecular oxygen and insert both the oxygen atom into the product. Carbon-carbon bond cleavage is entirely different. Here, if you are seeing the intradiol enzymes that cleave the carbon-carbon bond between the two hydroxyl group, whereas in the case of the extradiol enzyme that cleave the carbon-carbon bond adjacent to the hydroxyl group. So the product also entirely different. In one case we can get the diacid, and in one case we get the semi-aldehyde as a product. Among these two pathways, the extradiol cleavage pathway is a common pathway which is adopted by the nature. So let us have an insight into the active site of the intradiol dioxygenase. It is a iron 3 containing enzyme. So iron is in the higher oxidation state. In order to stabilize the metal in higher oxidation state, we need a strong donor. So it is employing two tyrosine moieties. One is located in the trigonal basal plane, and another one is located at the apical position of the coordination trigonal bipyramidal geometry. Whereas the remaining two sites are occupied by the trigonal basal plane was occupied by one histidine nitrogen donor as well as the hydroxide ligand. The hydroxide ligand, the origin of hydroxide ligand is from water because in enzyme they are also working under the aqueous conditions. So the origin of hydroxide may be derived from the water molecule. And the apical position, another one of the apical position that is trans to the tyrosine moiety is occupied by the histidine motif. So it is present in the Pseudomonas fluid bacteria and catalyze the cleavage of the carbon-carbon bond in between the two hydroxyl groups. Here the ion existing in nature, almost all the systems, the ion will exist in the high spin state, even it is plus 1 oxidation state, plus 2 oxidation state, or plus 3 oxidation state, whatever it is the oxidation state, generally the both activating enzymes generally having a high spin electronic configuration. We are seeing the extradiol enzyme. Extradiol, we have already seen that it is playing a same role, that is the degradation of catechol, but the pathway is entirely different. Here the active site is constituted by two histidine and one glutamate residue. The remaining positions are occupied with the level water molecule which are replaced during the course of the catalysis. Here it is having the ion in high spin D6 electronic configuration. The geometry around the metal center is either square pyramidal or it is a trigonal pyramidal or octahedral, that is depending upon the water molecule and the steric effect exerted by the metal center, the active site of enzyme. So again, we will come into the mode of ring cleavage. As we have already discussed, two different modes are possible. So two different products, one will end up with the two different products. One is the diacid, other one is the monoacid. So both the enzymes using share the same substrate catechol, but the cleavage products are entirely different. It clearly indicates that the mechanistic pathway is not same for these two enzymes, but are following different pathways to cleave the catechol. This is a common mechanism which is followed by these two enzymes. Both the enzymes with catechol and molecular oxygen at the center point, they will generate a alkyl peroxide intermediate by the accepting of two electrons. So depending upon the intermediate rearrangement, we will get two different products. In the case of the intradiol cleaving enzyme, we will have a acyl migration. This acyl group will be migrated to the peroxide oxygen and cleave the anhydride as a product that will cause an opening. And in another case, if it is undergoing the alkyl migration, that will lead to the lactone formation. The lactone will undergo CC bond opening and that will generate a different product. This is this common intermediate, but their rearrangement is entirely different. This is mainly dictated by the protein scaffold, which is wrapping around the active site. So we will know that in order to understand the mechanism of action, we have to get insight into the reactivity pathway. So that is, if you are employing the metalloprotein as your analyte, then we will find some difficulties to handle the enzyme because enzymes will work under only aqueous conditions, or we have to maintain some buffers also. And in addition to that, it's a macromolecule. It's a collective of all the effects, primary effect, secondary effect, tertiary effect, all together they join and conduct the reaction. So the understanding of the enzymatic mechanism again is a tough one. So how to get more insight about the mechanism of such kind of a biodegradation process? So one can easily simply what enzymes, their activity and everything mainly depends upon the active site. The active site, what the metal ion and as well as what are the protein residues which are bound with the metal ion. That is the main dictating the central part of the enzyme. So that is the key factor. So that will give the idea about how to understand the mechanism. So in such cases, transition metal complexes play a useful, highly useful tool to understand the mechanism of the enzymatic actions. So we can tailor-made the ligands also. In biological system, we are having tyrosine as well as the histidine immunosome carboxylate acid zonas. So in such cases, if we are doing synthetic analogous, we can tune the property, electronic property as well as steric property in a wide range. Instead of imidazole, you can introduce a pyrazole, benzimidazoles, pyridine, phenolene, but so on. Like that, you can extend. In addition to that, instead of carboxylic acid, you can use the phenolate donors as well as the ether donors, cyclic ethers and open chain ethers also we can introduce. By introducing such kind of donor arms, we can tune the electronic property. Once we are tuning the electronic bonding mechanism with the ligand to the metal complexes will changes. That will automatically tune the electronic property of the metal as well as the reactivity also. So by changing the electronic property and steric property, you can easily achieve the goal that is played by the enzyme. So the modeling can be easily further divided into two parts. One is the structural mimic, another one is a functional mimic. Structural mimic is nothing but we have to exactly duplicate the active site structure and spectral properties. And sometimes it may align with the redox behavior, but in most of the cases, the redox behavior may be varying, slightly varying. In functional mimics, we can duplicate the function. We can change the ligand donor arms. Instead of imidazole, we can put the pyridine. Instead of carboxylic acid, we can put any other of the donors. If it is doing the function, then fine. So that is the important one. So in order to gain more insight, so we have designed some of the ligands. That ligands also systematically vary different. We have tuned the electronic as well as the steric property systematically. They are saying it is a prototype of the ligand, the dipica. The dipica is nothing but a bisphenyl methylamine ligand, which is a well-known ligand. What we intended in this case, we have first ligand 1 and ligand 2, we have kept one of the pyridine as a constant along with the secondary amine hydrogen. So what we have tailored, we have modified another one. Instead of pyridine donor, we have introduced a ether donor. In the ether donor also, we have two choice. One is a open chain ether, and one is a cyclic ether. So in the second is L3 to L4, what we did, instead of pyridine, we introduced a imidazole donor function. We will not pyridine is a pi donor, whereas the imidazole is a sigma donor. So the properties are entirely different. The remaining portions are same, but the donor property is changing. That will affect the electronic property of the metal center. The another group of ligands, L5 to L8, here what we have did, instead of secondary amine, we introduced a tertiary amine by introducing one more pyridine, one more imidazole. So instead, the first four group of ligands, they are acting as a tridentate. The L5 to L8 are expected to give the four coordinate, give the four dentation for the complex formation. Quite interestingly, while characterizing the complexes, we are fortunate enough to get the crystal structure of the two of the representative complexes. The complex L2 is in which the tridentate ligand is facing capping around the metal center in a facial manner, as in the enzyme, and the remaining the chloride sites are replaced during the course of the reaction. It is unusual in the case of the complex L6. What we anticipated, we have provided the four donor site for the complexation, but it is acting as a tridentate ligand, again with the facial coordination, the metal center, and the three chloride ions are occupying the remaining octahedral positions. So our ultimate aim is what we thought: one set of ligands will act as a tridentate, another set of ligand will act as a tetradentate ligand. But both the cases, we end up with the tridentate coordination of the ligand donor. So what we did, but our ultimate aim was how to make the iron oxygen bond with the ether donor. So in order to bring that, what we did, this clearly indicates that the presence of, in the absence of a strong donor atom, the ether oxygen will make a bond with the iron center. So the same strategy, what we did, instead of reducing the ligand donor site, what we did, we have reduced the concentration of the chloride ion that would lead to the formation of the ether bound crystal. But in this case, what we are quite got different results. That is a dinuclear ion center is formed during the course of the reaction instead of the mononuclear site. But from the ether oxygen formation, we can come to the conclusion that the absence of strong electron donating atom, the ether oxygen will definitely bind with the metal center. This is the understanding of the crystal structure. So once we have isolated the 8 complexes, that library of complexes, after that we would like to study the interaction of the complexes with the model substrate. In order to study the catalog cleavage ability, we have chosen these 4 model substrates. They are changing in their steric as well as the electronic property. If they are having the methyl as well as the tertiary group, they will act as the electron donor as well as the tertiary group will furnish the steric hindrance around the metal center upon coordination with the ion center. Whereas in the case of the tetrachlorosubstituted derivative, that will act as an electron withdrawing group, and the steric hindrance also offered by the chloride ion, but it is not that much of what we are observing in the case of the distributed catalog. These catalogs are interacted with the above 8 complexes, and in the presence of the triethylaminosyl base, external base. So upon studying the optical spectral properties, we observe 2 different bands. We well know that the iron 3 complexes what we have generated all are pale yellow in color, but they don't have any DD signature. This is because of the Laporte forbidden transition. Because iron in the high spin D5 state, the high spin state iron don't have any spin allowed as well as symmetry allowed transition. So it won't exhibit any visible signature in the range of 400 to 1100. So for addition of catabalate dianium, we have pre-protonated the 2 protons using the triethylamine base. We can nicely see the 2 hindrance bands in the visible region. This clearly indicates that it is binding with our substrate is binding and giving the corresponding signature. They are almost appearing around 800 to around 500 nanometer region, the visible range. In addition to that, the band positions are not at all falling in the same wavelength. Depending upon the electron donor substituents or electron withdrawing substituent present in the catalog derivative, they are shifted to either blue shifted or red shifted. When we are having a chloride derivative that is observing in the highly shorter lambda, when we are having didestributed group, that is the band positions are red shifted to 800 to 900 nanometer range. All the complexes giving the same kind of signature when we interact with the catalog substrate. So we are studying the models for a redox active enzyme, so we should know the redox property of the complexes also. Redox properties we can study we are having a wide scope of experimental conditions. We can do modify the solvents and the temperature conditions, whatever we are implying that we can. But in this case, we have altered only 2 factors. One thing is the solvent, another thing is the our anion. In the first case, what we did, whatever the complex we get, as such, we have run the DPV and we got the CV as well as DPV. Upon interaction with the catalyte substrate, we observed two peaks in the differential pulse gram. This clearly indicates that one is corresponds to the iron 3 to iron 2 redox pair, another one is the oxidation reduction of the substrate. This clearly indicates that the substrate is donating definitely donate electron during the course of the reaction upon activation. So upon addition of the base to the catalyte added solution, the one band is disappearing, another only one peak is appearing. So this clearly also indicates that this complexes undergo reaction as well as the electron transfer is taking place with the substrate. Everything is clear. Suppose if you are seeing the potential, the EF values of the complexes 1 to 4 are little more negative compared to the 5 to 8, because here donor atom property as well as everything is changing. In one case, it is existing, it is having a furan oxygen donor bound molecule. Another case, the furan oxygen remains uncoordinated. So the behavior of the 2 set of the ligands are entirely changing. In another set of the experiments, what we did, we have changed the solvent. Instead of DMF, what we did, we used dichloromethane as a solvent. The solvent properties are entirely different. DMF is coordinating, having some coordinating ability, whereas DCM does not bound with the earth center. In addition to that, we have removed the coordinated chloride using a silver perchlorate as a chloride ion removing source. And we have generated the solvated species. So once we remove the electronegative chloride ion from the coordination environment, the Lewis acidic character of the metal centers are highly shifted to the positive potential. In the previous case, what we have seen, the EGA value that is observed from the DPV experiments showing minus 0.315 volt, and it is falling approximately around minus 0.3 volts. Whereas in this case, once we remove the coordinated chloride and replacing the DMF with the DCM, dichloromethane solvent, all the potentials are shifted to positive side. This is also highly one of the interesting factors we have to notice. So the solvent also playing in a major role in dictating the redox potential. So further, the prepared catalysts are applied for our ultimate aim to cleave the catechol, the presence of molecular oxygen. When the catechol adducts are generated and exposed to molecular oxygen, the molecular oxygen is supplied to the reaction solution by purging, and the optical changes are monitored with respect to time. And this is the very nice degradation of the band which is generated by the catalyte to ion 3, that is the LNCT band. That's the reason why it is having high intense. So these bands are nicely disappearing with the respect to time. So all the complexes after removal of the coordinated chloride ion and in the DCM solution, they react at a faster rate, and within 10 minutes all the reaction almost finished, and they are giving a nice yellow color starting complex solution in the QA. So the disappearance of the LFCD bands are monitored during the course of the reaction, and while we are plotting the time with respect to the 1 plus log of observance, we observe the linearity. This linearity is highly indicating that these reactions follow pseudo-first order conditions, because we are keeping the molecular oxygen concentration is 10 times higher than that of the concentration of the catalytic product. So also mimicking the enzymatic function in terms of the reactivity. So once the reaction is over, what we did, we have analyzed the product of the reaction. This clearly indicates that we are getting two different set of products. External cleavage products also we have observed, as well as internal product cleavage also. These are the self-oxidation products which are observed, but we are not mainly focusing on that, but we will focus mostly on the internal as well as external product cleavage as well as their ratios that we give the further insight into our mechanism. This is what we have already shown. This intermediate, if it is undergo alkyl migration, that will lead to the lactone formation. If it is undergo acid migration, that will lead to the intradiol product. So from the gas chromatographic analysis as well as NMR studies, that clearly reveals that oxygenation reaction generate both intra as well as extradiol product. So based on our observation as well as the characterization of the product, we have proposed a mechanism to explain the product distribution. So we have to give account for both the intradiol as well as the extradiol product formed during the course of reactions. So this intermediate, if it is a tridentate ligand, there are two possibilities of the enzyme substrate plus oxygen bound state. This, if it is undergo alkyl migration, that will generate the extradiol product. If the same intermediate is generating the undergo acid migration, generate the intradiol product. If the distribution is not occupied by the molecular oxygen, then we will replace the unknown from the coordination environment. That also leads to the formation of the intradiol product. So it's applicable only for the complex into 1 to 4. If you are taking the account of the complex into 5 to 8, then the possibility is entirely different. Here, if it is there is the possibility of the trend coordination, but in position behavior, it may exist as a 4-coordinated ligand. Both the tri-coordinate as well as the tetra-coordinated ligand form exist in equilibrium. That is given by the product yield, what we observe. So this is a ligand system. If you are having L1 to L4, that are giving the different ratio of the product. L5 and L8 that give the different ratio of the cleavage product. Here we have summarized all the data, the solvent effect as well as the anion effect and the product ratio. If you are seeing the complexes one with chloride and one with solvated species, in DMF it is giving mainly the intradiol product, whereas in the DCM it is giving the extradiol product. The ratio is very, very high. If you are having the percentage of intradiol product in the case of the optical pieces, but 71% of the extradiol cleavage is also observed. And the reactivity rate also high in the case of the solvent medium DCM. Whereas in the case of the second set of the ligands, the tetradentate ligands, so here we are having the different ratio of the products. In this case, what we observed, the intradiol cleavage product ratio is very high compared to that of the extradiol cleavage products. This clearly indicates that there is an existence of the equilibrium more towards the right hand side. That is the tetradentate coordination mode of the ligand is much more favorable in the case of the tetradentate ligands 5 to 8. Here also the reaction rate increases, but in this case, what we have seen, the external product cleavage ratio is amount is very, very low when we are having the ligands with the one more additional donor arm. So the tridentate coordination mode of the ligand is highly important for the to obtain the maximum yield of external cleavage, as well as the solvent also playing a major role. When we are having the solvent, coordinating solvent, that solvent will lead to the external product. When we are having the non-coordinating solvent, that is in the case of DCM, we will end up with the maximum amount of external cleavage products. So from the above things, one can easily conclude that the already there is a major amount of external product in DCM that we have seen in the table. When we are having a sterically left entering immunosuppressive donors that exhibit highly selective external cleavage products. Whereas in the case of the tetradentate coordinating ligand, we will have a major amount of internal cleavage products, not the external cleavage product. So the reactivity pathway is entirely shifting when we are employing the solvent as well as the coordination, increasing the coordination. So these are the findings what we observed. So next thing is I have to acknowledge before I have to left the platform for questions. I have to acknowledge these three persons who highly responsible for the present my positions. One is my PG and PG teacher, Dr. P. Sivasamy, and one is Professor Palniandavar, who introduced me to biomimetic chemistry. And that was further fueled by Professor Wong Nam. He is one of the pioneer biomimetic chemists who is involved in the generation of high valent metal oxo as well as the dioxin species. These three persons are highly responsible for our present current studies what we are involved. Thank you one and all for your kind attention. Now I leave the platform for questions and answers.
Thanks for your nice presentation, Dr. Sundararajan. There has been some clarification has been asked by students in YouTube. Slide number 31, I think.
Yeah, of course.
Yeah, and in this case of L1 F first system with solvent thrice, the reaction rate is 5.73. So whereas for L8 system, the reaction rate is 21, and for L6 system it's 48. So there is severe change in the reaction rate. So what may be the reason?
Yeah. So what is the reason for that?
Yes.
So these complexes are entirely different because here the coordination is mode is entirely different. The solution behavior we can't able to easily predict. Because solid state behavior, it is showing an uptight environment with the 3 chloride ion as well as the 3 nitrogen donors only. But in solution, 2 entirely different coordination modes are exist.
No, actually, in all the 3 systems, solution 3, when you compare L1, L5, and L8, all are with in
Yes.
solution state, but is the ligand system plays a vital role in the reaction rate?
Ligand system as well as solvent. Here, when we are having L8 solvent 3, it is a DCM solvent. L1 also DCM solvent only, but the coordination mode is entirely different.
Okay.
One case it is a tri-coordinator, another case it is a tetra-coordinate.
Okay. So,
in addition to that, if you are seeing the tri-coordinate system, which is undergoing very slow reactivity, that is giving the major amount of extra product.
Another question, for L3 system, the EI ratio is high. What is the reason for that?
EI ratio L3 system is a imidazole with pure, I think, open chain ether linkage. Again, the electronic property is entirely different. If you are seeing the rate, reaction rate, whenever molecules which are giving the slow reactivity, that is giving the higher yield of the extra product. If you are seeing the complexes 1 to 4, the complex 3 is reacting much slower rate in all the aspects, even with the solvents as well as the coordinating anion. It is reacting with a slower rate. 2 times it is decreasing, almost 2 to 2.5 times decreasing.
And another,
so the slower rate is can easily be explained by the bonding of the strong coordinating imidazole. When we are having the imidazole donor, imidazole will push more electron density to the metal center and decrease the Lewis acidity. So what would happen that would lead to increase the covalency between the ion center as well as the catechol. So that will reflect in the O2 binding reactivity also.
a third question from Arul from Gandhigram. So when if your talk is on biomimetic, but the solvent you have used is DMF and DCM.
It is not biologic. It is a biomimetic only. So we are mimicking the active site structure. Not exactly solvent. We can choose water as a solvent. But one thing is that ion complexes are more vulnerable for the aqueous environment. That will undergo sometimes decomposition in solvent, water solvent.
Thanks, Na.
Yeah. Is there any other questions?
Singaram sir, any other questions, sir?
No.
Shall we wind up?
Yes, ma'am.
Okay. Very well presented and explained, sir. Thank you very much, sir. Sundaraveli, sir. Let me invite our next speaker guest, Dr. K.K. Purushothaman. It's my duty to welcome Dr. K.K. Purushothaman, who has graduated both UG and PG in Gandhigram Rural University, Gandhigram, who has done his research in the same university. He has published around 34 papers in international journals with aggregated impact factor of 94.24 and 1,390 citations. He has published 3 book chapters and he was awarded JRF by UGC Government of India and GRI Research Fellowship by Gandhigram Rural University. His research interest is in the preparation of hybrid new materials for an energy conversion and storage applications. Now he is accepted to deliver a talk about the topic Nanomaterials for Supercapacitor applications. Welcome, sir. Purushothaman, sir.
Thank you, ma'am.
Kindly take over the session, sir.
Yeah, thank you.
Welcome, sir.
Yeah, very pleasant talking to all the participants. I'm going to talk about nanomaterials for supercapacitor applications. So this is what the overview about the presentation. Initially, we are going to see why we are moving towards energy storage devices like batteries and supercapacitors. So what is the meaning of that energy storage?
Sir, excuse me.
Yes, ma'am.
So your PPT is not in the view, sir. Purushothaman sir?
Yeah, maybe. Hello, ma'am. Is it okay now?
Okay, sir. Okay, sir. Please continue. Sir. Sir,
Hello, ma'am.
it's not visible, sir.
My screen is. Ma'am, is it visible now?
Not yet, sir. Okay, sir. Okay, sir.
Ma'am?
Okay, sir. Okay.
Go to slideshow.
Okay.
Okay, sir. Okay, sir.
Okay,
Please
fine.
continue.
So sorry for the technical delay. And this is what we overview about this presentation. Initially, we are going to see why we need an energy storage, what is the need of the one. So in that particular, we are going to see about supercapacitors and kind of electrochemical energy storage devices. So after that, we are going to see about the nanostructured electrode materials, why we are moving towards nanostructured electrode materials, what is the advantage of that one over a normal electrode materials, and some. Fully automated system. That means we are utilizing completely energy. The main reason for this technological advancement is due to the population growth. We all know that the population is an ever increasing one and increasing in a huge manner. So for that, we need huge energy. Our ever-giving energy source is nothing but the sun, but the sun can't shine the night. So we need energy storage devices. So in that, the major role played by batteries. But batteries is having lower specific energy. In the other side, you can see the high power device that is called capacitors. And this is called nothing but as rubber flag, which gives a comparison between all the energy storage devices. So there is a huge gap between batteries and capacitors. That gap has been filled by the device called supercapacitors, which is having the energy somehow equivalent to batteries and the power which is equivalent to capacitors. So this is having the properties of both the batteries as well as capacitors, and we call this one as an supercapacitors. So this is a small comparison between battery, supercapacitors, and capacitors. You just see the charging time. In the case of batteries, you need to charge more than 1 hour, the time lies between 1 to 5 hours. Whereas in the case of supercapacitors, the maximum time it is just 30 seconds. Whereas in the capacitors, the charging time is only in the range of microseconds. If you are comparing the lifetime of battery is about 1,000 times the charging and the recharging cycles, whereas in the supercapacitors there is a 10 power 6 times. This is typically having the behavior of capacitors. So the lifetime means, for example, in your mobile you are using battery, they are giving warranty for 1 year. 1 year means there is a 365 days. So what it implies that, for example, you are charging it for 2 days. Between 2 days means, so its lifetime is 365 divided by 2. That is what actually the lifetime of the batteries. If you are using supercapacitors instead of batteries, then its lifetime is 10 power 6. So we just multiply 2 into 10 power 6, then you can get what is the lifetime of your battery. So that is what the major advantage in the case of supercapacitors. Same if you are thinking about power, the capacitors are nothing but power devices. In the case of batteries, that is less than 1,000, whereas in the case of supercapacitors, that is equal to 10,000 watt per kilogram. This is opposite in the case of energy. In the case of batteries, the energy lies between 10 to 100 watt hour per kilogram, whereas in the case of supercapacitors lies between 1 to 10. So in the case of actual capacitors, it is less than 0.1 watt hour per kilogram. So this is what the comparison between batteries, supercapacitors and capacitors. And supercapacitors lies between batteries and capacitors. So actually there are two types of supercapacitors. One is called electric double layer capacitors. So purely based on the charge storage mechanism, they are classified into two types: electric double layer capacitors and pseudocapacitors. If the charge is stored through accumulation of charges between the electrode and electrolyte interface. You just see in this diagram, the charges are stored here. This is the charged state, positive and negative charges. This is creating a double layer. Whereas in the case of discharge state, this is in a random manner. So this is what we call it as electric double layer capacitors. So generally, the carbon-based materials like activated carbon, graphene, CNT, that will exhibit an electric double layer behavior. These are having very high conductivity and different resources, and the chemical stability is very, very high. This is non-toxic also. But the problem with this kind of electric double layer capacitors is this will give only very low specific capacitor. Or then you put electrochemical reversibility also. But the problem is having very short life cycle. And lithium actually exhibits higher specific capacitance, but the cost of that material limits its commercial application. Transition metal oxide with carbon materials. So metal oxide with carbonation material that is having high specific capacitance, longer life cycle, high energy as well as power densities. So this is called the hybrid supercapacitors. And in the case of supercapacitors also, depending upon the cyclic voltamograms, nowadays they are calling battery-like capacitors. So this is also coming under pseudocapacitor behavior. So in the case of cyclic voltamogram, if your probe is a pattern like a rectangular shape, that is called as a normal supercapacitors, like an EDLC behavior. Whereas if it is having acceleration and reduction peaks, that is called battery-like behavior. So we will discuss it later. What is the advantage of these supercapacitors? This is mainly used in power devices like military and aerospace applications, high power sensors, actuators, and electric hybrid vehicles. Nowadays in China, they are using supercapacitors in the electric hybrid vehicles practically. So this is what the typical structure of supercapacitor. This is similar to the battery structure. You just see, this is having two types of current collectors, maybe nickel foam, nickel foil kind of materials may be used as a current collector, graphite sheet. And after that, you are having your electrode material. This is what nanostructured electrode material. And in the middle, you are having separator like batteries and then electrode like that. So if you are arranging the supercapacitors, the similar on the another side, same kind of material means that is called symmetric supercapacitors. Whereas in one side you are using the transition metal oxide based material, in the other side if you are using carbon based material means that is called an asymmetric supercapacitor. So this is what a typical supercapacitor is. In the bottom you are having carbon, the in between separator. In the top you might have some carbon based material or transition metal oxide based material. If it is a transition metal oxide based material, then that is called as an asymmetric supercapacitor. Otherwise, that is called a symmetric supercapacitor. So why we are moving towards the nanostructured materials? So we all know that the nanostructured material means that its surface to volume ratio is very, very high. Surface area is also very, very high. So due to this property, there is the reduced dimension that will increase the contact between electrode and electrolyte. Same way, the morphology plays a dominant role in this case of electrochemical storage devices. Because depending upon the morphology, same material, for example, if you are considering nickel oxide, if it is with a nano rod structure, nano seed structure, or a hollow sphere structure, each morphology will begin in a different way. That will give different specific capacitance. Here, the morphology also plays a dominant role. For example, if you are taking a small puri, like what we call the honey puri, if you are just placing on hole in the top and then you are filled with your masala, honey, or curd, so without the pore, that is not possible to put all those things inside. The same way, that is what a typical structure of a hollow sphere. So the same way, if you are having pores in the outer side, automatically the ions will enter into that pore and that will access the inner surface of that sphere also. The outer surface easily accessed by the ions, and the inner surface also, if you want to access by the ions, means you have to create the porosity. So then only that ions will enter through that pores and that will access both the surface area. Automatically, the storage capacity will get increased. So the morphology plays a dominant role and porosity maximizes the accessibility area. But what is the problem with this nanostructured material? That is the release of hazardous byproducts while you are preparing the nanomaterial. Same way, the nanomaterials can easily interact with our biological system. So this is what the major drawback with this nanostructured materials. So this is the very basic and simple methods of preparing nanomaterials. Precipitation method, hydrothermal, and microwave methods. I think this is what a very simple method we can easily set up in our UG or PG laboratories. Then ball milling, spray pyrolysis, chemical vapor deposition, physical vapor deposition. There are a number of methods available for nanomaterial. Very simple and cost-effective method from our side is like precipitation, hydrothermal, and microwave. So the general characterizations before each nano samples if you are preparing it. That is the first thing is structural investigation. You made what kind of material have been prepared by you, with what base, by using X-ray diffraction analysis, and then by using FTA or FT round, depending upon your material, whether you are using carbon based or not. And then morphology studies can be made by using scanning electron microscope and high resolution transmission electron microscope. The topographical analysis can also be made easily. And energy dispersive X-ray analysis, X-ray spectroscopy will give you what is the combination of materials, what is the percentage of element present in your prepared material. You have to measure what is the surface area also, because surface area plays a major role. If surface area is high, that will accommodate a more number of ions on that one. We have already discussed about pore size, so we can study through nitrogen absorption, deabsorption, and the surface area studies. If you are considering about electrochemical studies, cyclic photometric analysis that will give activation and the reduction state, and also we can calculate specific capacitance by using CV analysis. Same way, galvanostatic charge discharge analysis can be made by using chronopotentiometry. The life cycle, same way, specific capacitance, energy and power density can be calculated by using chronopotentiometry analysis. The AC impedance analysis will give you the charge transfer resistance. Here, the resistance also is an important thing, because depending upon the resistance, the power delivery will vary. If it is having lower charge transfer resistance, then it may act as a very good power device. So next, we are going to see about supercapacitor behavior of nickel oxide and nanostructures prepared by using hydrothermal method at different temperatures. Just this is an SEM image of nickel oxide prepared at 120 degrees Celsius, 140 degree, 160 degree, and 180 degrees Celsius by using hydrothermal method. And then that has been calculated at 300 degrees Celsius. So this is prepared at 120 degrees Celsius, 140 degrees Celsius, 160, and this is at 180. If you are closely observing this one, at 160 degrees Celsius, a sheet-like structure has been formed. So this is what an formation mechanism of a nano seeds. Here we have used sodium doped diesel sulfate as a structural agent, and by using urea hydrolysis through hydrothermal method at 160 degrees Celsius, that will create laminar missiles, and that will lead to formation of nano seeds-like structure at 160 degrees Celsius. At different temperatures, that will create different structures. For example, at 180 degrees Celsius, this is seems to like thick nano plates. If you closely observe it, that will give teeny nano rods. That assembled nano rods is seems to like a small thick plates. So depending upon the preparation temperature, the morphology varies. Structural and thermal properties have been studied by using X-ray diffraction analysis, thermobiometric analysis, and FAR analysis. From the XRD studies, we can reveal that that created NaO structure according to the JCPS code number 780643. From the thermobiometric analysis, we can observe at what temperature the nickel hydroxide may change into nickel oxide. We just observe this curve. Between room temperature to 200 degrees Celsius, the water and alkali chain of SDS surfactant has been removed. And between 200 to 355 degrees Celsius, that is phase change occurs from nickel hydroxide to nickel oxide, and that will lead to huge weight loss. That is somehow 27% weight loss has been observed in this region. So based on this one only, the 300 degrees Celsius have been fixed for annealing. And FAR also confirms the nickel oxide vibrations. At the same time, the OH vibrations also observed in the case of FAR studies. You can clearly observe there is an oxidation and well indicated reduction peaks from cyclic photometric analysis. Again, this is for nickel oxide prepared at 4 different temperatures. So this clearly shows that oxidation and reduction speed. The sample prepared at 160 degrees Celsius gives a maximum current. So that indicates that this is having higher specific capacitance. So this is the CV between 2 millivolts per second to 45 millivolts at a different scan rates. Same if you're seeing a charge discharge analysis, this is a discharge curve of same nickel oxide sample prepared at different temperatures. So the taken by nickel oxide sample prepared 160 degrees accumulates is having higher specific capacitance. So nickel oxide prepared at 160 degrees Celsius exhibit maximum specific capacitance of 567 farad per gram at the discharge current rate of 1 ampere per gram. The same discharge has been made for different current densities, namely 1, 2, and 3. The curve is shown here. That is the effect of current density. So in all the currents, nickel oxide nano seeds prepared at 160 degrees Celsius exhibits maximum specific capacitance. If the current density increases, the capacitance seems to like decreases because at higher current densities, the accessible area will decreases. And same IL drop also get increases. The specific capacitance can be calculated using that relation C is equal to I del V divided by M into del V. That I is the discharge current, del V is the discharge time, M is the mass of the electrode material, del V is the window. Why that particularly the material prepared at 160 degrees Celsius exhibits a maximum specific capacitance? We can study that photosis analysis. Actually, this exhibits the surface area of 155 meters per gram. At the same time, it confirms that this is having a mesoporous structure. There is the porosity in the range of 20 nanometers and all. So the ions can easily enter through this pore, and that will enhance the specific capacitance in the case of samples prepared at 160 degrees Celsius. So the impedance analysis also confirms the lower charge transfer resistance for the samples prepared at 160 degrees Celsius. So this is what we call as a solution resistance. So the typical equivalent circuit is written here. This is the solution resistance, and the curve here is called charge transfer resistance. That will cut at the x-axis. Interpolation of that one will cut at the x-axis. That is called charge transfer resistance, and this area is called Warburg impedance. So the RCT value of sample prepared at 160 degrees Celsius is 5.574. This is lower and comparing with the other samples. And the cyclic stability is a much more important thing because this will decide whether your material will make commercial impact or not. So in our system, This is retain 97% of the capacitance up to 1000 continuous cycles at the rate of 3 ampere per gram. So this is also a good result and cyclic stability also. So initially the first work is about nickel oxide, this is pure transition metal oxide, and next is about a hybrid electrode material, that is the copper oxide with reduced graphene oxide copper. So the copper oxide with reduced graphene oxide, this is also prepared by using the graphene sheet in the bottom side and the copper oxides are anchored on the graphene sheet side. So this is what we call the hybrid composite material. Again, the structural features are formation of copper oxide. So this is clearly confirmed. This is a hybrid nanocomposite formed in this work. The cyclic voltammetric curve at a different standard is shown here. You just compare this one with the previous pure nickel oxide. So in the case of nickel oxide, the pure nickel oxide, you are having accretion and reduction. Please just see the curve structure. Whereas in the case of hybrid, so this is somehow like a quasi-rectangular shape. Even you can observe the acceleration and the reduction speed here also, because the pure EDLC of carbon-based materials are having a very good rectangular shape curve. So this is an in-between, this is having the behavior of both the things. So according to charge discharge profile, you can easily find that this is also having that kind of behavior, because the pure EDLC will have a triangular shape. This is in between the thing. And the specific capacitance, again, the specific capacitance for charge discharge curve is a 326 farad per gram at the rate of 0.5 ampere per gram. So due to addition of graphene oxide, this is showing 100% stability even up to 1500 cycles. There is no degradation has been observed up to 1500 cycles, 100% stability is there. Same way, if you are checking this charge transfer resistance, the value is 2.47 ohm because of that presence of reduced graphene oxide. So we have prepared that hybrid composite based symmetric supercapacitor. So we have used cell-covered material as a separator and nickel foam as the current collector. This is an asymmetric device. In both the sides, we have used copper oxide and graphene as the electrode materials and anode as well as cathode. So this is the typical 3V curve for different scan rates between 2 to 10 millivolt per second. Same way, this is the charge discharge curve between 200 milliampere gram to 2000 milliampere gram. And the specific capacitance derived from this DCT measurement is 69 farad per gram at the current density of 0.2 ampere per gram. And the energy density is 13.8 watt hour per kilogram. Power density is 59.6 watt hour per kilogram. So this is somehow approaching closer to their batteries. And while we are discussing about the preparation of nanostructured material, we have discussed that will liberate hazardous byproducts. If you want to overcome that issue, you have to move towards the cleaner synthesis of nanomaterials. And we have made an attempt to synthesize vanadium oxide-based carbon nanocomposite by using green synthesis method. So green synthesis method means we have to use the naturally occurring reagents, vitamins, sugar, plant extract, like that. So that will lower the toxicity and will reduce the environmental impact of the byproducts. So based on this idea, we have used actually Dextron as the green agent. Generally, Dextron will create a spongy-like structure. So the metal salts are added with dextran. After the constant stirring at room temperature, we have added the metal salts with the dextran, and the pH has been increased up to 10. And the homogeneous solution has been aged for 2 days or 3 days. And precipitate has been absorbed from the cone and passed several times by using double distilled water. And that has been calcinated at a particular temperature, and that will give you metal oxide carbon nanocomposites. So again, like the previous two studies, we have made both the exfoliant FT Raman to confirm the formation of V2O5, and in this case we have prepared carbon. So that is also giving the same kind of a D and G band like the graphene structure. So this again confirms that the carbon has been formed in this composite. So this is what the Fe3M on HRTM image of the prepared copper oxide. Prepared vanadium pentacid sample. You just see this is an ultraline-like structure. You can closely observe this one. This is somewhat seems like a plasma one, and individually seems like a ultraline-like structure. If you are taking HRTM images, in that end point you can observe carbon lake. So this is actually a carbon-coated ultraline-like structure, and that selected area diffraction analysis also confirms there is some diffuse spots in this case. So some amorphous carbon is present in this material along with the crystalline V2O5. So CV curves has been recorded in the potential range of minus 0.1 to 0.75 volt by using 0.5 volt K2SO4. And that will lead the specific capacitance of 362 farad per gram, the scale rate of 2 millivolt per second. Again, if you are seeing it here, the specific capacitance decreases with increasing in the scale rate. Because if you are increasing the scan rate, the accessible area will decrease again, and that will result in the lower specific capacitance. So again, the charge discharge curve, and this will give you the specific capacitance of the 470 farad per gram in the potential range of minus 0.1 to 0.8 volt. Because here there is no such higher IR drop. If you are increasing the current, the IR drop is also get increasing. That is the reason why the capacitance decreases if you are increasing the current density also. So if you are observing the stability in this case, from the maximum that gives 92.3% over 2250 cycles, whereas if you are considering the initial point, this is having higher stability. So in general, we are discussing it with the initial capacitance, but in this case, we are discussing with the maximum fusing capacitance. So due to the presence of carbon, the stability increased enormously, because the major problem with this vanadium pentacid is its stability. Theoretically, its specific capacitance is much more higher, but the stability, lack of stability of this material reduces its actual application. Through this extra usage, we have obtained a huge stability for this vanadium pentacid based materials. Whereas in the case of asphalt material, that is without carbon, it is having only 45% at 800 cycles. Just 45% at 800 cycles, huge reduce in the cyclic stability. So the charge transfer of resistance of this material is 0.93 ohm. This gives the charge transfer resistance. This is the solution resistance. This is the overlap impedance area. So we have prepared vanadium pentacid and carbon composite based supercapacitor cell. This is again a symmetric supercapacitor cell. The CV curve has been recorded for 2 millivolt to 20 millivolt per second. Same way the charge transfer, charge discharge curves also given here. So we have prepared vanadium pentacid based supercapacitor cell by using electrodes has been prepared by using like a Doppler plate method, and the device has been run for the potential range of 0.0 to 1.2 volt, and that will give the specific capacitance of 101 farad per gram at the scale rate of 2 millivolt per second, and that will the energy density of 10.3 watt-hour per kilogram at the current density of 1 ampere per gram. So in all of the studies, we have used nickel foam as the current conductor, and slurry, ethanol-based slurry method has been used to prepare the electrode. In general, we have used 1 milligram as the electrode material. So this is simply in comparison with other results. So in this case, we just observe in our study by using the focusation based article method, we have radial fantastic and component opposite. And this gives a very high specific capacitance, 470 farad per gram, while comparing with the other works. So in this case, this is 484, and they have used reduced graphene oxide. The cost of that one is very much higher. We are comparing with the Nextron and all, and we are having 100% cyclic stability even after 2000 cycles. Whereas in the RGO case, this is only 70% at 1000 cycles. We obtained a very good cyclic stability during this green synthesized composite. And first, I would like to thank the organizers, management, and particularly Dr. Singham for giving this opportunity. And the now session is open for questions.
So thank you, Dr. Purushothaman. So from your presentation, there are some of the questions from the audience. So is the electrolyte same as that of electrolyte we use in electrochemicals?
Yeah, in the case, actually, we are having three types of electrolytes. That is aqueous-based and organic electrolytes. And usually, aqueous electrolytes, we are using a KOH or NaOH that is having a very high conductivity. Organic electrolytes is having lower conductivity, whereas ionic liquids is having a higher voltage range. The voltage range is about 4 volt. So there are three different types of electrolytes on that: aqueous-based, organic-based, and ionic liquids.
Whether it is possible to use carbon materials which have D and G band for supercapacitor application?
Yeah, I think in the study also we have discussed about the materials which are having G and D and G bands. Even without D and G bands, you can use amorphous carbon also, carbon darts also. So all the types of carbon materials can be incorporated with any transition metal oxides, and that will enhance the conductivity, and that will reduce the shrinkage of the material also, because during that pseudocapacitor, the structural change will occur, the volumetric change will occur in the case of transition metal oxides. If you are using carbon-based material, that may restrict that one, that will enhance the lifetime also.
And third question, whether all the transition metal ions can be used for supercapacitor application, or else is there any special cases?
Yeah, nowadays they are trying with all the transition metal oxides, but if you are saying it is having higher oxidation and reduction states, then that is really good for supercapacitor. If it is, for example, vanadium is having higher oxidation and reduction states, right? So this specific capacitance is higher, theoretical capacitance.
So how about...
So there is one formula, by using that one you can calculate the theoretical specific capacitance of any transition metal oxide, and based on that one you may choose your material.
So how about cerium? Because cerium has highest oxidation state, and also manganese, it has highest oxidation state of +7. Can it be used?
Hello?
Yeah, can you hear me?
Yeah, no.
Yeah, cerium and manganese have highest oxidation state, right? Cerium has +3 and +4, and also manganese has +6 and +7. Whether it can also be used for these kind of supercapacitor applications?
There are quite a lot of works are going on in this manganese, because it's having a very good specific capacitance, theoretical capacitance. There are a number of works are going on based on that material. Even cerium oxide is also reported with a number of researchers. In both the materials, already number of papers are published.
Thank you, Dr. Purushothaman.
Thank you. Thank you very much for giving this opportunity.
Thank you, Purushothaman. This is Sambat Kumar.
Yeah, thank you.
So I would like to extend my heartfelt thanks to the management of SSMIIT principal for providing us an opportunity to conduct a virtual seminar for the 2 days. And then next, I would like to thank all the resource persons for their valuable inputs. And also, I would like to thank all the participants from various institutions and organizations. And finally, I would like to thank Mr. S. Damodaran, Mr. A. Amaladiban, and Mr. Bonaraja for their timely help and support to conduct the seminar in a successful way. Finally, I would like to thank all the technical team for their support in this regard. Thank you very much. For the participants, the feedback link will be sent to your registered mobile number within a few minutes. Thank you so much.